We've now seen that a lot of what we're used to doing for derivatives carry over pretty nicely to these functions of several variables. And in fact, we've utilized pretty much all the standard rules for finding derivatives. But there is a specific type of extension that has to be noted with regards to the chain rule, right? The chain rule is something that you kind of get a sense of what it is or how it can be used in single variable calculus, but it's not until you get to, let's say, what we're about to do, that you really see the scope and the importance of the chain rule. And so now when we think about the chain rule, so let's say you have that y is a function of u, and let's say u is a function of x, and we're going to assume that f and g are both differentiable on their appropriate domain, right? So we don't have to worry about things not being differentiable. Well, so this is how you can essentially describe the relationship between x and y using two equations. If we wanted to use one equation, then it would look like this. We would just have y equals f of g of x. And then it's of this form, I think, that we're most familiar with the chain rule, right? Where we say, okay, well, we take the derivative of the outer function, we evaluate it at the inner, and then we multiply by the derivative of the inner, right? So, I mean, outer and inner, not the, not the best terms to use to describe this relationship, but it works, right? It's a nice little thing that you can use as a reminder. So this is what we are used to as far as the chain rule. But also, there's another version of the chain rule where we can actually represent the derivative of y with respect to x as the product of two derivatives, right? I mean, there are two derivatives here, right? But the one that I'm going to write down involves the variable u. Notice there is no u down here. It's just everything is in terms of f and g, and f prime and g prime. Well, over here we can write, and especially if we use our Leibniz notation, we could say, well, if I take the derivative of y with respect to u, so if I take that derivative first, and then if I were to multiply it by the derivative of u with respect to x, right? So du dx, at least symbolically, right, we can see where, if we treat what's on the right purely as fractions and just symbolics, right, then we can reduce this, and you can see how it's reasonable to think that dy dx can be expressed as this product. And even though we don't really use this form, again, when we're working with just a function of a single variable, when we get to a function of several variables, this form is what we need to keep in mind. And there's a really nice visualization that can show you the relationship between all these variables. And let me show you what that relationship now is. Because again, let's kind of say it out. This is saying that y depends on u, but then u in turn depends on g. So I can actually visualize that hierarchy like this. I could put my uppermost, dependent variable on top there, and then I could right below it just kind of link it to its immediate the variable that it immediately depends on. So just put a u there. And then this equation tells me that u directly depends on x. So then I can do another line here, and then I have an x. And then imagine all these variables changing. Imagine that, say, x changes. And then when x changes, typically u will change. And it will change at a particular rate. And I can indicate that rate by doing this, du dx. But then when u changes, again, typically y will change. I say typically because if these just happen to be constants, then nothing changes, right? But let's assume that these are non-constant functions, and when x changes, it affects u, and then u will change, and when u changes, it affects y, and all these variables, right, the dependent ones, not the very one at the bottom here, right, because notice x doesn't depend on anything else, so this is truly an independent variable. You can think of your u as like an intermediate variable, but then all of these have an impact on y, and then what we want is essentially, as far as derivatives are concerned, oh, there should be a du. We want to know ultimately at what rate is this variable, right, going to change with respect to this variable, right? And we want to represent that rate of change as in terms of these derivatives. So this is sometimes referred to as a tree diagram, right? That it's a very useful tool. You use tree diagrams in so many different scenarios. But yeah, so this is how you can visualize it, where you have, again, essentially single variable functions. Now let's extend it, and we'll do it in a gradual sense. Eventually, we're going to get to a very general statement of the chain rule, and I'll just warn you, brace yourself. It's not that bad. It's just it has to encompass all the possibilities, and when you try to do that, sometimes the results and the theorems get a little messy. But let's take a look at case 1. Right. And again, there is no true order to this. I'm just saying, okay, let's look at this case. So suppose I have now a function of two variables. Z depends on x and y, but then suppose x in turn is a function of t. So then suppose x is a function of t, and so is y is a function of t, like that, right? So let's start with the visualization, right? Let's see if I can set up, before I even put any derivatives or anything, let's just see if we can set up the hierarchy that would illustrate this sort of these variables and the relationship amongst them. So what do? Well, we start with this one. So we have our variable z. Everyone loves z. And then this equation tells me that z depends on what x and y are, right? So I'm going to do two branches, one for each of the variables that this variable depends on. So one for x and one for y. So I'm going to do that and that, right? But then when I look at these two equations, it tells me, or these two equations tell me that x depends on t and also y depends on t. So I need another set of branches, one from x going down to the letter t, and then one from y going down to the letter t. So this is the tree that demonstrates this relationship, right? So, you have all the equations, but this is kind of a visual. So t is truly our independent variable. It does not depend on any other set of variables. The x and y are kind of the intermediate, right? So these are like the cogs, so for instance, when this changes, this one will change, and then when this changes, this one will change. So eventually, by invoking changes in t, you're going to affect z, but it goes through these two intermediate variables, x and y. So again, what we want to be able to use or eventually say is, if I change t, how or what rate will z change? Because remember, our derivative at its heart is a rate of change. All right, so in order to see how this rate of change of z comes about, this is where I'm going to put some derivatives. I'm going to label each of these branches with different derivatives, right? And I'm going to use everything in terms of the partial d, right? So, for instance, along this branch, when x changes, z will change at this rate. So dz dx. And then along this branch, when y changes, z will change at that rate. Along this branch, this one will reflect the rate of change of x with respect to t. So I'm going to do dx dt. And then you might know what's going to come here. This branch is going to reflect the rate of change of this variable with respect to this variable. So dy dt. All right. So again, not only does the tree this application of a tree reflects again the dependencies amongst variables, and then it also uses the branches to reflect the different rates of change, right, that are involved. So ultimately, since there's only one true independent variable here, we would like to know what is the rate of change of z with respect to t. What is that equal to? Well, think about it. There are two ways that changing t will affect z. One way is through x. So for instance, if I were to multiply these two, right, that will account for some of the changes in z, or yeah, I'll say this, but really we're talking about rates. But this product here will account for some of the rates of change of z with respect to t, but then the rest of it will be accounted by if I were to multiply these two. So if I go back and look at this and say, okay, if I want to find the rate of change of this variable with respect to this variable, the chain rule says multiply these two. If I have this kind of dependency, this is what it says. You have to account for all the ways you can start from a z and get to a t, right? So from this dependent variable to this independent variable. And each time you go from one branch to the next, you do a product. Think of it as an and. So this and this. Every time you take an alternate route or path to go from a z to a t, that's an or. And, you know, in many instances, you can think of an or as a plus and an and as a times. So here's how it's going to play out. So the rate of change of z with respect to t is equal to the product of dz dx times dx dt. So that's one path. Or, and that becomes a plus, the other path now is dz dy times dy dt. So dz dy times dy dt. Now, this is where you start to see that you can't really treat these as fractions. Here is why. Because if you just say, oh, let me just cancel these out and cancel these out. Well, if you treat them as fractions, you realize that, oh, something is messed up. Because on this side, you essentially have one dz dt. And then on this side, you'd have a dz dt here, and then another one here. So we can't really, we don't think of it as really canceling out. These are differentials, right? And they are used the sum essentially is used to represent the single rate of change. And so this would be the version of the chain rule that would apply to a situation like this. Right? Now, let's do an example just to illustrate it. And then I will go to a case 2 where we have slightly more variables to work with. All right, so let's do an example of this. And with the example, like when you have specific functions here, I will show, and I'll do it with this example. I'll show you that there is essentially an easier way to envision what's going on and to actually compute the required derivative. So let's say we have something like this: x times e to the x squared y. So let's say that's my function z as a function of x and y. But then let's go ahead and say that x is a function of t, and then let's say y is another function of t. Let's say the square root of t. All right, so there we go. What I will do is the first method that I'll show you is using this particular rule. And we can even set up our tree diagram and actually put the different partial derivatives on each branch, and I'll show you how it all comes together. And then I will do the same problem in an alternative way, which you might say, well, yeah, that's definitely the easier way to do it, but then I want to show you that we end up with the same result, right? And then hopefully it will start to solidify the understanding that we can't treat these as fractions, right? Okay, so here's our method 1. So method 1, using the tree diagram and this formula that I just stated. So I'm going to put my again, I'm going to make the tree a little bit bigger, right? Just so I can label things correctly. And then those like this. And then we'll have our x and our y. And again, we will have t and t, right? T and t. All right, so along this branch, it is, now maybe what we should do is we can switch notations and use the subscript since it will fit on the branch a little bit better. So z sub x, I have to differentiate this with respect to x. And actually, let me do this. Let's do the all the derivatives that we need off to the side, and then I can label it. So if we do z sub x, I have to use my product rule because this function depends on x, as does this function. So I have to use my product rule. And I'm treating y as a constant. So it's the derivative of the first times the second plus the first times the derivative of the second. Now, because it's an e, I'll first get back the e to the x squared y, and then I need to multiply by the derivative of what's inside with respect to x. With respect to x, we treat y as a constant, so I'll bring down the y and then apply my power rule to the x squared, and I'll get 2xy, right? So that's what it looks like. And it might be a little easier to write if we factor out the e to the x squared y, and then that leaves the quantity 1 plus, and then I have a 2x squared y as this term, right? Okay, so not too bad. So I'm going to go ahead and put that partial on this branch. So that's my z sub x, and that's the e to the x squared y. Oh, my y fell out of the exponent. I hope it didn't get hurt. So e to the x squared y, and then times the quantity 1 plus 2x squared y. All right. So there we go. So that's that one. Now let's do our z sub y. That's the partial derivative that's going to go on this branch. Again, you don't have to label the branches, but let's decorate the tree. Let's make it all festive. So we have z sub y, and with now differentiating with respect to y, we get to treat the x as a constant. So this x is a constant multiple. It comes down. I still have to use the chain rule on the e, so I'll have e to the x squared y, And now when I take the derivative of the exponent with respect to y, I bring down the x squared, and then the partial derivative of y with respect to y is a 1. So this one's a little bit simpler. We end up with x cubed e to the x squared y. So that's what I'll put on this branch. And like I said, in the spirit of festivity, we can decorate our tree with different colors. So we got x cubed e to the x squared y. Okay, right. So these are now the partial. These are our regular partials with respect to x and y of the z. Now the other branches. Now we have to differentiate x with respect to t. So again, maybe I'll do this on this side. So dx dt, that one's a whole lot easier. This is just, you have one variable here and then another variable here. So it's just this one ends up being 2t. And we can also do dy dt right away. This is a regular square root. When we differentiate it, we're going to get 1 over 2 root t. So let's see. So x sub t will be 2t. And then y sub t will be so along this branch, it's 1 over 2 root t. All right. So now we have the tree diagram set up, and what I would like to write down is the partial derivative of z with respect to t. So dz dt, formulaically, it's going to be z sub x times x sub t plus z sub y times y sub t. So again, multiply the blue and the green, multiply the red and the white, and then add them together. So it looks like this. So we have this expression here, which is e to the x squared y times the quantity 1 plus 2x squared y, and then times 2t, and then plus, so that's one path, right? That's one way that z is affected by t. An alternative path is through the red and the white, so take the x cubed e to the x squared y, and then multiply by 1 over 2 root t. Right? And that's what we have, right? Now, ultimately, when we write down something like this, right, when we have dz dt, we would like to have our partial derivative, our derivative here, we would like it to be solely in terms of t, right? In other words, we want our rate of change to be solely in terms of the variables that are at the lowest level, the ones that are truly our independent variables, right? I mean, x and y they're kind of a mixture, right? Because they affect z, but then they are affected by t, right? So we would like this final answer to be solely in terms of t. In fact, I notice here, let me just put a little line there that separates it so that we don't think that these are in any way related. I mean, they are related, but I don't want these expressions to get mixed up down here. So how do we do that? Well, we know what x is. Remember, x is t squared, and y is the square root of t. So if I wanted all of this to be in terms of t, then I could literally put t squared in for x and the square root of t in for y, and then I would have my dz dt in terms of t, right? In terms of the truly independent variable. So it looks like this. If I square t squared, I will get t to the fourth, and then times the square root of t, and then in parentheses I'll have 1 plus, and then I'll have 2, again, t squared is t to the fourth, and again times another root t, and then times 2t, so that's there, and then plus, now here we have to cube it, right? So t squared cubed, that's t to the 6th, and then the e has the same expression there in the exponent, the t to the 4th root t, and then times 1 over 2 root t. So that's it. Now, I mean, we can go through, there are things we can do to simplify this, but I just wanted to show you, again, setting up the tree, finding the partials, multiplying and adding the appropriate terms, and then writing your final answer in terms of your, essentially, your lowest level of variables, right? So that's one way to do it. The other way, let's say we go back and we want to find dz dt and everything. So we're essentially using 3 equations to describe the relationship between these 4 variables, z, x, y, and t. But do we really need 3 equations? I mean, why don't we just cut out the middle 2, the middle pair? What if we just took out the x and y, right? And wherever there's an x, why not just put in the t squared? Just do it. Just do the substitution at the start. And then wherever there's a y, just why not put in the square root of t? In other words, why not write z explicitly as a function of t? So do this. Do the, say that z is equal to t squared, and then e to the, do the same thing in the exponent, t to the 4th times the square root of t. Now, because I am essentially doing this at the start of the process, and then I will still have to do my derivative, I'm going to simplify this. I didn't simplify it at the end because we were pretty much at the end of the process, but here I'm showing you an alternative way to get to the same answer. So then we have t squared, and then we have e to the, now adding these exponents gives me t to the 9/2, right? So that's what it looks like. So method 2, let me start it right down here, is, yeah, basically eliminate x and y. Since I want this derivative, then yeah, if possible, express z as a function of t. So then we end up having, so again, let's write it down. It's the t squared. See if I can remember it in my old age here. So it's t squared e to the t to the 9/2, right? And we have to differentiate this. So now you could use your regular dz dt. I'm just gonna, continue using the partial notation. So here I would need my product rule. So then I'll end up getting 2t times the e, which is that, and then plus, then I'll have my t squared times, and then I have to differentiate the e, so that will require the chain rule. So I'll have the e to the t to the 9/2, and then times the derivative of the inner, so the derivative of that power function is 9/2 t, and then subtract 1, that gives you 7/2, right? So it turns out, and I encourage you to verify that if you take this and go ahead and simplify, kind of like what we did here, you will end up with an expression that looks like this, right? But clearly, this is the easier method computationally, right? Why not, again, just cut out the middle variables, the x and y, write down a single equation that gives the relationship between z and t, and then take the derivative. But the power of the first method isn't necessarily that it's going to make our, basic calculations easier. What this, let me go a little further back up. what expressions like this will allow? It will allow us to symbolically express a single rate of change as the sum of the products of several rates of change. And you might say, well, why would I want to do that? Trust me, we're going to want to do it at least once in the future, right? So we're going to grit our teeth and get it done. All right. So let me just kind of wrap up and show you a case too. So now suppose we have something like this, where we have z as a function of, let's say, x and y. But now suppose x is a function of r and theta. And suppose y is also a function of r and theta. Let's see what the tree would look like for this, and then we'll essentially write down the two expressions for partial derivatives, right? So here's the tree. Again, we start with our topmost variable, right? Notice that z does not affect any other variable, so we put that one at the top, and then we put the variables that have an immediate effect on z, x and y, and then we just keep branching. And so now we're saying that x and y depend on r and theta. And so so x and y, they each depend on r and on theta. And so now let's say this is it. So our tree is like, 2 levels deep. This is level 0, this is level 1, this is level 2. I'll use the subscripts, right? A little bit faster, a little bit more efficient, and just label each branch with the appropriate rate of change or derivative. And it's always the derivative of this variable, the one that's like directly above, with respect to the one that's directly below, right? And then here, this will be the partial derivative of x with respect to r, and then this branch will represent the partial derivative of x with respect to theta, and do the same thing on this side, just switching the x's to y's. So then this is the partial derivative of y with respect to r, partial derivative of y with respect to theta. So now if I wanted to write down a single expression that would represent z sub r, what I would do in this tree, I will find all the paths that start with a z and end with an r, and I will highlight those in blue. So we'll go along here, obviously, and then along here. That's how and like almost working backwards, this is how r can affect z. It could also affect it by going along here and then along there, right? So with that, if I multiply these two, right, going from one branch to the next, that will, and then add the product of z sub y and y sub r, in total, that will represent the rate of change of z with respect to r. So it looks like this. So we'll have z sub x times x sub r. That's along, that path. Or along this path, z sub y times y sub r. So z sub y times y sub r. And that's the expression that represents the rate of change of z with respect to r. If I wanted it with respect to theta, I could do that too. I'll indicate those with red. So that's where I would go along that path. And then let's say get to that path. And then, or along this path. And then, or branch, right? So using the ones in red, our z sub theta is equal to z sub x times x sub theta plus z sub y times y sub theta, right? And I mean, and that's the chain rule. Or more specifically, another version of it. And again, you can see how this can change. I could have a lot more variables here, and then I could have a lot more variables in, again, for each of the equations. So my tree can become rather luscious. It's like, lots of leaves and branches on this tree, right? To wrap it up, let's just state the theorem in its fullest, right? Again, so this is the theorem, and this is the multivariable version of the chain rule, right? And there are several ways it can be stated, but this is what it is. Suppose z is a function of, let's say, x1, x2, xn. I don't know how many of them, but lots of them. And that each xi, so each of the x's, and that each xi is in turn a function of, and I'll just use t's, but I'll say maybe there are lots of them, like t1, t2, This number, the number of x's and the number of t's don't have to be the same. So I can say I'll use a different subscript here, right? So we have z, which depends on lots of these, and each of these depends on a lot of these. What we would like to write down is, so for instance, what would be the rate of change of z with respect to t1? Or what would be the rate of change of z with respect to t2, and so forth. So if that's the case, assuming, again, each of these functions are differentiable, so I'll just say assuming differentiability, so that all the partial derivatives that we need will work. So assuming differentiability, if I wanted to find the partial derivative of z with respect to, let's say, ti, any one of these, so dti, what I would have to do is take the partial derivative of z with respect to this first variable, so x1, and then multiply it by the partial derivative of that variable with respect to the t that I'm interested in, the ti. And then do that for each of the x's, right? So then dz dx2 times dx2 over dti, and I'll do my dot plus until we get to the nth x. So dz dxn times dxn over dti, right? So like I said, it's a lot when you try to write it down. When you try to write it down generally, you have to allow for any number of variables here and then other variables here. But even this is still not completely general, because then what if each of these ti's, or each of these t's were now, let's say, functions of r, like r1, r2, r up to rq or something, and then it just gets crazy, but in a good way, right? It's crazy good. So that's the chain rule. This one, all the other rules like the product and the quotient, it's pretty much the same no matter how many variables you have. But the chain rule, it's this idea of functions being dependent on other functions. That's where we really needed to mention this discussion. And I promise you, we will use this in the future to come up with another important result. So it's just a new result after new result, fun after fun, but that's the Pandora's box of mathematics, right? It's never ending. You just keep unraveling other things. So let's continue unraveling other things in the next video. I'll see you then.